Hello, and welcome to the Exponential Smoothing tutorial series. In this tutorial, we'll demonstrate the double exponential smoothing in NumXL. For the sample data, we are using weekly demand volume for a hypothetical product. Holt's double exponential smoothing is best used with data that exhibits stable trend over time and no seasonality. So let's examine the data set for the trend assumption. Using Excel's built-in chart function, draw a trend through the data. The weekly demand data shows a significant downtrend. This is good for double exponential smoothing, so let's begin and select the cell D10. Type in the function name equals DESMTH, open parentheses, in the cell or in the equation toolbar. Once you find the correct function, click on the FX button located on the left side of the equation toolbar. This will invoke the function arguments dialog box for the double exponential smoothing function. Using the function arguments dialog box, specify the input cell range and lock the reference by pressing F4. In the order field, specify 1 for the time order in the series, or simply put the first observation in the input series that corresponds to the earliest date. For the level smoothing parameter alpha, you can type in a value between 0 and 1, or reference an existing cell. For this example, let's reference the value in D1 and lock the cell reference by pressing F4. For the trend smoothing parameter beta, you can also type in a value between 0 and 1, or reference an existing cell. In this example, let's reference the value in D2 and then lock the cell by pressing F4. For enabling and disabling the function's built-in optimizer, you can type in a true-false value or reference a cell in your worksheet. Let's reference the cell D3 and then lock the reference by pressing F4. For the forecast time, we'll be forecasting the value at the end of the input data. So set T to 0, or better yet, reference a cell in a column A, so we can change it after the end of the input data, and then lock the cell for column movement by pressing F4. For return type, leave blank or type in 0 for forecast, and then click OK. The function returns NA since we don't have enough data, so copy the formula to the cells below it, even after the end of the sample data. Don't worry about the empty cells picked up after the end of the input data. The function will ignore them. Let's plot the one-step smoothing forecast. Although this is an out-of-sample forecast, which means it uses data available up to the forecast time, not the whole sample, the double exponential smoothing is converging to a linear trend line using the whole sample. The multi-step forecast of the double exponential is a sloped line, as is shown in the plot. To quantify the overall forecasting power of the double exponential smoothing, we will use 3 functions: mean squared error, mean absolute percentage error, and mean absolute scaled error, as is shown in cells D4 to D6. Let's set alpha to 10% and leave beta at 20%. The mean absolute scaled error has improved by 4%. Now let's set both alpha and beta to 10%. Great! The mean absolute scaled error has improved by another 4%. Let's examine this scenario. Set alpha to 25% and beta to 15%. Ouch! The mean absolute scaled error surged to 80%. How about 15% for alpha and 10% for beta? Alright, the mean absolute scaled error went down about 5%, but it's not the best scenario. How about we set alpha to 20% and beta to 10%? Nope, it worsened. One last scenario. How about 20% and 5%? No, we don't have any change this time. Finding the optimal values for alpha and beta is not a straightforward process. Fortunately, NumXL has a built-in optimizer for finding such values, as you will see in the next tutorial video. That's all for now. Thank you for watching.